This story is about a place where sound has no right to exist, about a space in which everything we are used to calling large, cities, continents, entire planets, shrinks to a point on the margins of a vast and very slow map. I will speak of a silence that lasts billions of years, and of how, in that silence, light quietly is born, fades, and is born again. No sensations, no loud words, only what is actually there. If you try to picture everything we will be talking about all at once, even thinking becomes difficult. Hundreds of billions of stars in our galaxy alone. Hundreds of billions of galaxies in the region we are even capable of seeing. Light traveling to us for millions and billions of years, which means every night sky is already a gaze back into the past. Entire regions of space whose light will never reach us, because space itself between them and us is receding faster than a photon can travel. Matter that we have learned to name, broken down into atoms and described in equations, accounts for at most 5/100ths of all the energy in the cosmos. The rest, invisible. Dark matter holds galaxies in their shape. Dark energy stretches space itself, and neither one allows us to catch it in any telescope. And in the middle of all this, our small star, our small planet, and that short interval in which each of us manages to live a life and ask quiet questions. And how do you feel when you think about this? Does such an abyss make you feel smaller? Or, on the contrary, does something in your chest open up and become calmer? What matters more to us, to find peace beside this immense silence, or to try to solve it? There will be no direct answer in this story. There will be facts, long pauses, and a pair of questions we will try to answer together. Listen, this story is about just that. Imagine for a moment that you have found yourself in open space, not in a science fiction film with the hum of engines and the shimmer of neon nebulae, but in true interstellar space as it actually is. There is no air, no landmarks, and not a single sound. Not simply the silence we know from a quiet room or a night forest, but the absolute physical impossibility of sound as such. A sound wave is the vibration of a medium, propagating through matter. In a vacuum, there is nothing that can vibrate, which means sound simply has nowhere to exist. If a star exploded beside you, you would not hear a single sound. Not because the explosion is too far away, but because it is physically impossible. Interstellar space is not an absolute vacuum in the strict sense. Matter is present, but its concentration is negligibly small. On average, a cubic centimeter of interstellar medium contains only a few atoms, whereas the same volume of ordinary Earth air contains trillions. This is almost a void, and it is precisely what makes space simultaneously so stable and so cold. The temperature of the interstellar medium in most regions drops to a few degrees above absolute zero, the threshold at which the thermal motion of particles is almost completely stilled. And yet within this apparent torpor, processes are constantly at work. Atoms collide, hydrogen molecules form, and denser clumps of gas slowly gather. In the darkness between stars, enormous molecular clouds drift, whose dimensions can reach tens and hundreds of light years. By Earth standards, their density is negligible, but it is precisely in these diffuse clouds that the material for future stars lies dormant, not yet ignited, not yet existing, but already inevitable. A person placed in the middle of interstellar space would not see any majestic glow of the galaxy familiar from artistic illustrations. The sky would look almost completely black, and the stars, sparse, distant points, separated by distances that are nearly impossible to grasp with the imagination. The nearest star to the sun lies at a distance of more than 4 light years, and light travels at roughly 300,000 kilometers per second, completing 7.5 circuits of the Earth's equator in a single second. And even at this speed, it is not enough to cross the interstellar distance in less than 4 years of continuous travel. Our galaxy, the Milky Way, contains more than 100 billion stars, and its diameter is about 100,000 light years. A beam of light, traveling without stopping, would take 100,000 years to cross it from edge to edge. The Sun itself moves around the galactic center, completing one full orbit in roughly 230 million years. This period is called the galactic year. On the scale of the universe, motion never ceases, but it is stretched in time to such a degree that millions of years compress into a single instant in cosmic terms. Gas clouds slowly contract under gravity, density grows within them, and temperature rises. Interstellar silence can persist for tens of millions of years before a new star ignites somewhere within it. The silence of space is not the absence of events, but the consequence of enormous distances and physical laws that do not permit the propagation of sound in a vacuum. Radiation also propagates between stars. X-rays, gamma quanta, and radio waves pass through space with almost no obstruction. It is thanks to this that astronomers can observe distant objects. Light that reaches Earth from distant galaxies may be older than the solar system itself. When we look at the night sky, we see the past. Light from the nearest stars travels toward us for years, from more distant ones for thousands and millions of years. To gaze into space is always to gaze backward in time. But how large is this silent void? What lies beyond a horizon that is impossible to imagine? The understanding of the universe's scale changed gradually through discoveries that each overturned the previous boundaries of conceivable space. In antiquity, people believed that stars were fixed to a solid celestial sphere. Later, it became clear that Earth occupies no privileged position, and the Sun is merely one among a countless multitude of stars. But even this could not prepare people for what astronomers discovered at the beginning of the 20th century. Edwin Hubble looked through a telescope and saw what overturned the entire picture of the world. What had been considered a nebula within our galaxy turned out to be a separate stellar world, an independent galaxy more than 2 million light-years away from Earth. In the 1920s, Hubble showed that the Andromeda Nebula was an independent system, comparable in scale to our own Milky Way. This discovery instantly pushed the boundaries of the known cosmos to previously unimaginable limits. The observable universe is the region of space from which light has had time to reach us since the beginning of cosmic expansion. Its radius is about 46 billion light-years, and its diameter is nearly 93 billion light-years. These numbers exceed the age of the universe in light-years, and the reason is expansion itself. While light was traveling toward us, the distance between source and observer continued to increase. The age of the universe is estimated at approximately 13.8 billion years. It was Hubble's observations that laid the foundation for understanding this expansion. He established that the light of distant galaxies shifts toward longer wavelengths, and the farther the galaxy, the faster it recedes. This relationship entered the history of science as Hubble's law. The observable universe contains hundreds of billions of galaxies, each comprising billions, and sometimes hundreds of billions of stars. If you try to picture this number, even a rough estimate of the stars in the observable region alone yields a value exceeding the number of grains of sand on all the beaches on Earth. Our galaxy belongs to the local group, stretching roughly 10 million light-years, a structure that, in addition to the Milky Way, includes the Andromeda Galaxy and several dozen dwarf systems. Beyond that extend even larger formations, galaxy clusters, superclusters, and ultimately a giant cosmic web of filaments, nodes, and vast voids between them. If you look at the distribution of galaxies on large scales, it resembles a web. Between dense nodes and filaments lie vast voids containing very few galaxies. The boundary of the observable cosmos is defined not by a wall or a physical barrier, but by a horizon of visibility. Beyond this horizon, extensions of structures may exist, but their light has not yet reached Earth. Perhaps the universe is significantly larger than the observable region, and some cosmological models admit the possibility of its infinity. But where do the stars themselves come from? Where does their story begin? In the coldest and darkest corners of the galaxy? In the coldest place in the galaxy, where there is almost nothing, What will shine for billions of years is slowly being born. This happens inside giant molecular clouds scattered along spiral arms. Their temperature is only 10 to 20 kelvins, a state only slightly different from absolute zero. The basis of these clouds is molecular hydrogen, mixed with traces of helium and heavier elements synthesized in previous generations of stars. By Earth standards, the density of matter here is negligible, but compared with the surrounding interstellar vacuum, it is high enough for gravity to begin its slow work. Any unevenness in the distribution of matter becomes the seed of a process. A region where the gas density is slightly higher than average begins to attract additional matter to itself. Sometimes this process is triggered by an external impulse, a shock wave from a neighboring supernova explosion or the collision of two clouds. Gradually, a condensed fragment forms, which begins to contract under its own gravity. With each cycle of contraction, the temperature inside it rises. Gravitational energy is converted into thermal energy. Thus, a protostar arises, an object that does not yet shine through thermonuclear reactions, but is already heated to significant temperatures by the force of its own contraction. Around it forms an accretion disk of gas and dust, the very material from which planets may subsequently form. If the mass of the forming object is large enough, the temperature at its core reaches several million degrees. Under these conditions, thermonuclear fusion begins. Hydrogen starts converting into helium, and the radiation pressure produced balances the gravitational attraction. The protostar becomes a full-fledged main sequence star, a stable source of light and energy capable of existing for billions of years. This was the path taken by our Sun approximately 4.5 billion years ago, having formed in one of the arms of the Milky Way. Probably other stars were being born nearby at that time. Some of them have long since left that original cluster and are now scattered throughout the galaxy. Not every gas fragment becomes a star. If the mass is insufficient, the object becomes a brown dwarf, an intermediate body between a planet and a star, in whose interior only brief synthesis reactions may occur, but stable hydrogen burning never begins. Inside accretion disks, meanwhile, there is life of their own. Dust particles collide and clump together, gradually forming ever larger bodies, planetesimals, the embryos of future planets. In regions of active star formation, hot young stars ionize the surrounding gas, causing it to glow. This is how emission nebulae arise, one of the best known of which is the Orion Nebula, where dozens and hundreds of young stars are forming right now. Star formation does not occur evenly throughout the galaxy. It is concentrated in the spiral arms, where gas density is higher. Density waves passing through the galactic disk compress clouds and trigger new cycles of gravitational collapse. Thus, generations of stars succeed one another. Some complete their existence, ejecting matter enriched with heavy elements back into the interstellar medium, while others are only just forming. The iron, oxygen, and carbon, of which Earth and all life on it are composed, were synthesized in the cores of ancient stars and scattered by supernova explosions. It is thanks to this continuous cycle that the chemical diversity without which life would have been impossible came to be. Around many of these stars, planets orbit, and some of them are not so unlike our Earth. For a long time, the only known planets were the bodies of the solar system. It was theoretically assumed that other stars might also have their own systems, but no direct evidence of this existed. Everything changed toward the end of the 20th century. In 1995, astronomers detected a planet around another star for the first time. Around the star 51 Pegasi, a gas giant was discovered orbiting so close to its star that it seemed impossible by the then current theoretical understanding of planetary system formation. This discovery immediately showed that the diversity of planets could be far broader than expected. Thousands of such worlds have been found since then, and each has its own story. The majority of confirmed exoplanets have been discovered by the transit method. When a planet passes across the disk of a star, its brightness drops slightly, and this faint pulsation is recorded by sensitive photometers. The Kepler space mission made a decisive contribution to this catalog, identifying thousands of objects of the most varied sizes in orbits. Among the discovered worlds, there are so-called hot Jupiters, massive gas giants located far closer to their stars than Mercury is to the Sun. Their orbital period is sometimes only a few days, and the temperature of their atmospheres reaches 1,000 degrees. There are also super-Earths, planets whose mass exceeds Earth's by several times, but remains significantly less than that of Neptune. Some may possess a dense atmosphere and oceans, while others are dry, rocky bodies with extreme conditions. Worlds located in the habitable zone, the region around a star where temperatures allow liquid water to exist on the surface, are of special interest. In the TRAPPIST-1 system, several Earth-sized planets have been found, some of which are located precisely in such a zone, and these objects have become the subject of detailed studies. However, being located in the habitable zone does not by itself guarantee habitability. Atmospheric composition, magnetic field, and stellar activity can radically alter surface conditions. Many red dwarfs have powerful flares capable of gradually destroying the atmosphere of nearby planets. Some exoplanets orbit binary stars, receiving light simultaneously from two suns. There are also freely drifting planets, ejected from their systems by gravitational interactions, and now wandering through interstellar space without any host star. The atmospheres of distant worlds are studied using spectroscopy. When a planet passes across the disk of a star, some of the stellar light is filtered through its atmosphere, and analysis of the spectrum makes it possible to determine the presence of water vapor, methane, carbon dioxide, and other substances. The James Webb Space Telescope has significantly expanded the possibilities of these observations, opening access to molecules that were previously beyond the sensitivity of instruments. Statistical estimates show that most stars in the galaxy have at least one planet, which means hundreds of billions of planetary worlds may exist in the Milky Way. But in some of these systems, there is something far stranger than planets, something from which not even light escapes. The event horizon is not a wall. You cross it without noticing any barrier, and then you can never return. Black holes were long perceived as almost fantastical objects, and their existence was predicted mathematically long before direct observations. The theoretical foundation for describing them was laid by the general theory of relativity, formulated by Albert Einstein. The equations of this theory admit solutions in which gravity compresses matter to a state from which not even light can escape. A black hole arises as the result of the collapse of a massive star. When the nuclear fuel in its core is exhausted, radiation pressure can no longer resist gravity. If the mass of the remnant exceeds a certain limit, the contraction becomes irreversible, and an object forms with an event horizon, a conditional boundary in space-time beyond which light can no longer escape. The event horizon is not a solid surface. It is merely a boundary of causality. For an external observer, everything approaching the horizon appears to slow down and redden due to gravitational redshift. But for the falling observer themselves, crossing this boundary occurs without any sharp change in immediate sensations. The size of a black hole is determined by its mass. The radius of the event horizon for a non-rotating black hole, the Schwarzschild radius, is approximately 3 kilometers for an object with the mass of the Sun. If the Sun were suddenly to contract to such a radius without changing its mass, Earth's orbit would remain completely unchanged. Only the sunlight would be gone. Black holes exist in different classes: stellar ones, with a mass of several to several dozen solar masses, and supermassive ones, located at the centers of galaxies, whose mass reaches millions and even billions of solar masses. At the center of the Milky Way lies a supermassive black hole known as Sagittarius A. From the character of the orbits of the stars surrounding it, its mass was estimated, and it was confirmed that the center of our galaxy is occupied by a compact and extraordinarily massive object. In 2019, the first real photograph of a black hole shadow was published, an image obtained through the joint efforts of the Event Horizon Telescope project. It related to the object at the center of galaxy M87, and later a similar photograph of Sagittarius A was presented. These observations confirm the predictions of general relativity under conditions of an extremely strong gravitational field. The LIGO and Virgo detectors recorded gravitational waves arising from the merging of black holes, ripples in the fabric of spacetime, propagating at the speed of light. This very discovery was direct confirmation of the existence of black holes and opened up an entirely new type of astronomical observation. Stephen Hawking proposed the idea that black holes are capable of emitting faint thermal radiation due to quantum processes at the event horizon. This Hawking radiation leads to a very slow evaporation of the black hole, a process that for astrophysical objects takes intervals of time incomparably greater than the current age of the universe. The internal structure of black holes remains the subject of theoretical research. Classical physics postulates the existence of a singularity at their center, but quantum effects may alter this description. It is precisely at the intersection of general relativity and quantum mechanics that one of the main unsolved frontiers of modern physics lies. Black holes play an important role in the evolution of galaxies. The mass of a supermassive black hole correlates with the mass of the galaxy's central bulge, indicating their coevolution. Active phases accompanied by powerful energy outflows can influence the formation of new stars. A black hole is not the breakdown of the laws of physics, but their ultimate expression. Under conditions of strong gravity, space and time behave differently, but remain subject to mathematical description. Black holes are only one component of galaxies, but galaxies themselves are also islands in an ocean, slowly moving toward each other. Our galaxy and the Andromeda Galaxy have been steadily approaching each other for many billions of years, and their encounter is inevitable. The Milky Way belongs to the spiral type of galaxy. Its flat disk carries spiral arms where regions of active star formation are concentrated. At the center lies the bulge, a denser, spherically symmetric structure. Beyond the disk extends the halo, populated by old stars and globular clusters. Besides spiral galaxies, there are elliptical ones, systems with a smoother shape, almost devoid of cold gas and producing almost no new stars. Their population consists mainly of old stars. Irregular galaxies have no clear symmetry. Their shape is often explained by the gravitational influence of neighboring systems. Galaxies do not exist in isolation. They form groups and clusters. Our local group, stretching roughly 10 million light-years, includes the Andromeda Galaxy, the Milky Way, and several dozen dwarf systems. Andromeda is approaching us at a speed of about 100 kilometers per second, and in a few billion years a collision is expected. This process will not be instantaneous. It will take hundreds of millions of years. The stars and galaxies are so far apart that direct collisions between them are unlikely, but gravitational disturbances will profoundly alter the orbits and overall structure of both systems. Such mergers are often accompanied by bursts of star formation, and the central black holes may merge, generating powerful gravitational waves. On even larger scales, galaxies unite in clusters, between which lies hot intergalactic gas emitting in the X-ray range. One of the largest known formations is the Laniakea supercluster, within which our local group is located. Its size is measured in hundreds of millions of light-years. The motion of galaxies and their internal dynamics have long indicated that visible matter constitutes only a part of their mass. The speed of stars at the edges of galactic disks turns out to be higher than expected when accounting only for observable matter, which indicates the existence of an additional gravitational component, a massive and dark halo enveloping each galaxy. And yet the greater part of their mass is invisible. It cannot be detected by any telescope. More than a quarter of the universe consists of something that cannot be seen, detected by light, or registered by any known instrument. Only gravity reveals its presence. The first evidence of this mystery appeared as early as the 1930s, when Fritz Zwicky was studying the dynamics of the Coma cluster. He noticed that the speeds of galaxies in this cluster were too great to be held by visible mass alone, and proposed the existence of dark matter, creating additional gravity. At the time, this hypothesis seemed incredible to many. Later, a similar effect was discovered in spiral galaxies. Rotation curves showed the speed of stars at the periphery of the disk does not decrease with distance from the center, as it should when accounting only for visible stars and gas. Instead of the expected decline, the speed remained nearly constant, compelling evidence for the presence of an invisible, massive halo around each galaxy. This halo neither emits nor absorbs light in any appreciable way. It can be detected exclusively through its gravitational influence on visible matter. Dark matter is not composed of ordinary atoms. It does not form stars, does not participate in chemical reactions, and does not interact with electromagnetic radiation in the way familiar matter does. Its nature remains the subject of investigation, one of the main unsolved mysteries of modern physics. Gravitational lensing provides another way to register dark matter. Massive objects curve spacetime, altering the path of passing light. By observing distortions in the images of background galaxies, astronomers can reconstruct the distribution of invisible mass. This manifested particularly clearly in the study of the Bullet cluster. Analysis of gravitational lensing showed that the main mass of the system does not spatially coincide with the hot gas, and this serves as a strong argument in favor of dark matter as an independent component. By current estimates, ordinary baryonic matter accounts for only about 5% of the energy content of the universe. Dark matter accounts for about 27%. The remainder is associated with dark energy, a component responsible for the accelerated expansion of the cosmos. Dark matter is distributed unevenly. It forms gravitational scaffolding in which galaxies subsequently form. First, dense regions of dark matter arise. Then ordinary gas accumulates within them, which under the force of gravity contracts and gives birth to stars. Within the Milky Way, dark matter forms an extensive halo, significantly exceeding the size of the visible disk. The mass of this halo is many times greater than the combined mass of all the galaxy stars, yet it remains completely invisible to any telescope. In the silence of space, among stars and voids, there exists a component that cannot be seen directly, but it is its gravity that shapes the large-scale structure of the universe. But even what we can observe is only a part of the whole. Our view of the universe has a horizon. To look at a distant galaxy is to look into the past. Where we are looking, that galaxy no longer exists in its present form. The boundary of the observable universe is not a wall or a physical barrier, but a limit determined by the speed of light and the age of the cosmos. We can only see those regions from which light has had time to reach us during the entire span of cosmic evolution. The age of the universe is approximately 13.8 billion years, yet the radius of the observable region, about 46 billion light-years, is significantly greater than this figure in light-years. The reason is the expansion of space. While light was traveling toward us, space itself between source and observer continued to stretch. The most distant observable radiation is the cosmic microwave background, the relic glow of the early universe. It arose approximately 380,000 years after the beginning of cosmic expansion, when matter had become sufficiently diffuse and the temperature had dropped to a level at which photons could finally propagate freely without being immediately absorbed by the dense plasma. Until that moment, the universe was opaque. Light constantly interacted with charged particles. After recombination, photons set out on a journey that continues to this day. Today, the temperature of this relic radiation is about 2.7 kelvins, a barely warm remnant of an era when all matter was compressed into an incomparably hotter and denser medium. Small fluctuations in this temperature in different directions carry the imprint of the initial density inhomogeneities from which galaxies and clusters later grew. Satellites such as Planck have provided a detailed map of the relic background and have made it possible to refine the parameters of the cosmological model. Due to the accelerated expansion driven by dark energy, some regions of space are already receding from us faster than the speed of light. Not because objects within them are moving through space faster than light, but because space itself between us and them is stretching. This does not violate special relativity, but it means that light emitted by these objects today will never reach us. In the far future, many galaxies now accessible to observation will disappear beyond the event horizon, and the cosmos will appear significantly emptier to any imagined observer within the local group. The James Webb Space Telescope is detecting objects that existed only a few 100 million years after the beginning of cosmic evolution, systems at the earliest stages accessible to us. These observations refine models of the formation of the first stars and galaxies, opening up a picture of the universe in its youth. The boundary of the observable is not the boundary of existence. Beyond it may extend space vastly exceeding the visible region in volume. Measurements of the relic radiation indicate that the geometry of space is close to flat, meaning there is no significant curvature at large scales. The observable universe is a cross-section of reality, limited by the speed of propagation of information, and every photon arriving from the depths of space carries within it information about the state of matter at the moment of its emission. And this very gaze is itself a journey in time, because time in the cosmos behaves very differently from everyday life. Near a massive body, time flows more slowly. This is not a metaphor. It is a fact, without accounting for which satellite navigation systems would not function correctly. According to the general theory of relativity formulated by Albert Einstein, gravity is not the familiar force pulling bodies toward each other, but the curvature of space-time itself. Mass and energy alter the geometry of this structure, and objects move along curved trajectories, following its bends. From this, it also follows that the flow of time depends on the strength of the gravitational field. Near massive objects, time slows down. This effect is called gravitational time dilation. The stronger the gravitational field, the more slowly clocks run compared to a distant observer. In the vicinity of a black hole, this effect reaches extreme values. But gravitational dilation manifests itself far more modestly as well. Even on the surface of Earth, time flows slightly more slowly than in orbit. The difference is negligibly small, but it is measurable and is accounted for in the operation of GPS navigation systems. Direct confirmation that the theory of relativity describes real physical processes. Velocity also affects the flow of time. Moving at high speed relative to an observer, clocks run more slowly. This effect has been confirmed by experiments with atomic clocks and particles in accelerators. Time in the universe has a direction determined by the thermodynamic arrow. The observed increase in entropy sets the irreversibility of processes. This manifests in the evolution of stars, in the expansion of the cosmos, in how structures gradually become more complex and then degrade. The age of the universe, approximately 13.8 billion years, has been determined by several independent methods, including analysis of relic radiation and observations of distant supernovae, which made it possible to establish the fact of accelerated expansion. Our Sun has existed for about 4.5 billion years and is roughly in the middle of its life cycle. Ahead of it lie several more billion years of stable radiation. Galaxies also have their own temporal history. By observing distant systems, we see them in a young state, highly active, forming stars at a significantly greater intensity than now. Over time, their structure becomes more ordered, the pace of star formation slows, and their appearance becomes calmer. On the scale of galaxy clusters, time manifests in mergers and dynamical relaxation. Gravitational interactions gradually redistribute energy in orbits, and this process can take billions of years. If the accelerated expansion continues, the density of matter will decrease, and stars will gradually complete their existence. After extremely long intervals of time, only compact remnants of ordinary matter will be left: white dwarfs, neutron stars, and black holes. Some theories admit the decay of protons themselves in an even more distant future, which would ultimately lead to the disappearance of all ordinary matter. But such processes relate to timescales incomparably exceeding the current age of the cosmos. But all these processes are not only history, they are happening right now, at this very second. In the core of the Sun, a colossal quantity of hydrogen is converted into helium every second. In doing so, part of the mass becomes energy, according to a relationship derived by Albert Einstein. And this continuous flow of energy sustains the luminosity of the star, providing the warmth without which life on Earth would be impossible. In other regions of the galaxy, right now, in dark molecular clouds, the slow gravitational contraction continues. Protostars are gradually heating from within, and at their centers, the moment of thermonuclear ignition is steadily approaching. The moment when radiation pressure will finally balance attraction and a new source of light will blaze in the cold dark. At the same time, somewhere the life of massive stars is drawing to a close. When heavy elements in their cores are exhausted, radiation pressure can no longer resist gravity. A collapse occurs, followed by a supernova explosion. In these moments, heavy elements are synthesized, which subsequently scatter into the interstellar medium and will enter the composition of new stars and planets. At the centers of galaxies, supermassive black holes continue to accumulate matter. Where actively infalling matter forms an accretion disk, powerful jets of particles arise, extending for thousands of light years and exerting an influence on the entire surrounding environment. Even in the relatively quiet Milky Way, the central black hole, Sagittarius A, remains the gravitational core of the system. On large scales, the expansion of the universe continues. The distances between remote galaxies are increasing, and this process, invisible locally, manifests in the redshift of light from distant objects. In the local group, the Andromeda Galaxy is steadily approaching the Milky Way. Their gravitational fields are already influencing each other, though the main event is expected in billions of years. Cosmic rays, high-energy particles born in supernova explosions and in the active nuclei of galaxies, permeate interstellar space, never ceasing their movement for an instant. The cosmic microwave background continues to fill all of space, gradually cooling as the universe expands. Its temperature today is about 2.7 kelvins and is slowly declining. This is the echo of the earliest era, which never falls silent, only grows ever quieter with each billion years. Within the solar system, unceasing processes are also at work. Planets move along their orbits. Comets return to the sun after long wanderings in the cold outer regions. Asteroids collide, and the solar wind permeates space all the way to the most distant frontiers of the heliosphere. On Earth, we measure time by the change of days and the rotation of the planet. But in a wider context, this is merely one tiny gear in a colossal mechanism working without stop. Somewhere in the depths of the universe right now, black holes may be merging. Their merger generates gravitational waves radiating through space-time. Perhaps in millions of years, these waves will reach the region of space where future observers will be located. The invisible halos of dark matter continue to hold galaxies together and guide their movement, not interacting with light, but tirelessly determining the structure of all that is visible. Stars are slowly changing their composition and brightness. In some systems, planets are currently passing before the disks of their stars, causing a barely noticeable decrease in brightness. Events recorded by automated telescopes and adding to the catalogs of exoplanets. In dark molecular clouds, protostars have already formed, still hidden by dust, but in time they will ignite and become new sources of light in the night sky. If you look at the universe as a whole, it is never completely still. There is no moment of absolute rest. Even in the interstellar void, particles move and radiation propagates. The birth and death of stars, the approach of galaxies, the expansion of space, the fading of the relic glow, all of this proceeds simultaneously, without pauses or interruptions. On the human scale, these processes are almost imperceptible. The night sky looks calm and unchanging. But behind this apparent stillness lies a colossal dynamic system, living by the laws of gravity, thermodynamics, and quantum physics. The cosmos continues its existence and development, regardless of whether we observe it or not. And right now, in the silence of the night, somewhere in a distant galaxy, a new star is being born. And somewhere else, another is completing its journey. Please write in the comments how this story resonated with you. I really do want to understand whether it reached you. What do you think? Is dark matter some entirely new, invisible substance? Or is it that we simply do not yet fully understand gravity itself? And also tell me, do you prefer a horizontal video format or vertical for your phone?